again, I didn't get quite as far as I mentioned last time. I just barely started talking about extensive versus intensive variables, which are very simple. It's high school level, I know. We're going to do high school stuff today. But one of you asked me a little bit of a better definition, and I did not have one, but I thought of one. I thought I was so clever. So if I say to you, hey, what's, like on your homework, what's an extensive, what's an intensive? Is this extensive, is this intensive? Like on your homework, right? Here's what I thought to do. Okay. Is this, and by this, I mean whatever this is, it should have a unit, right? Is this extensive? Let's put an X. Okay, X unit, 5 moles, 3 liters, right? Okay, so the question is this, and this comes with a unit, is it extensive? The way to answer it is, does this number go up if you have more of the thing? Does X go up if you have more of the thing I'm asking about? That's extensive, right? So real easy. Now, where it gets a little hard, though, like on your homework, is I've thrown you some curveballs, like R times T and stuff like that. So, obviously, these are extensive. Entropy is the one you probably aren't quite familiar with. Again, I've thrown you some X factors on the homework. Intensive, one of the harder intensive ones, the ones I'm going to try to play games with you, are densities. Notice I didn't say density. Density, you're used to mass by volume. I said densities. There's all kinds of densities. You can make anything a density if you think about it. And those are going to be intensive. But the way to recognize that is, here, let me just wipe this out here. No eraser. They used to put erasers in here, but they would just disappear within a week, so they just put paper now. Okay, so a density is usually going to be 2 extensive things divided. And think of extensive as like a minus sign. So a minus, and think of intensive as a plus. If you multiply things that are positive or divide things that are positive, they stay positive. That's another way of saying they're intensive. So let me, sorry, the board is actually kind of hard to use. So think of that as a positive, and if you are manipulating units and everything's intensive, then the result is intensive. Just like if you multiply positive numbers together, the result stays positive. Negatives are the X factor, right? And negatives can be a little funky. So, for an example, if I divide 2 negatives, I get a positive. Or if I divide 2 extensive factors, mass divided by volume, those are 2 negatives that give a positive. Those 2 extensive variables divided give me a positive intensive result, right? Densities are intensive. So that's just a homework help. Note that you rarely, I can't think of a single example of saying a intensive variable divided by an extensive variable. I don't think I've ever seen that. There's no gas constant, there's no variable I can think of that does that because it doesn't make sense. Temperature divided by moles, and that's a constant. No, that doesn't make sense because that means that I can have more temperature with more moles, and nothing like that happens. So anyway, a little homework help. Sorry, I was struggling a little bit last time to cover all this stuff. Okay, so we're done with that again. High school level is to more high school level, but with at least maybe slightly more interesting. I want to introduce the concept of when I do this, that means I'm done with this, by the way. And what I'm going to talk about now are okay, I have to just write this out before I say it. A phenomenological model, I have no idea if that's spelled correctly, and I really don't care. I ought to, but I don't. Get your money back. Phenomenological models are models that just make sense. And I build these models to try to get something else out of them. So what I'm trying to do is get you the idea of what we do in this class. I'm going to write some equations that are phenomenological models, again, mathematical models that just make more sense. And then I'm going to do weird things to them and try to get new information out of them. And I'm going to do 2 examples, and let me start with temperature. Okay, so we're back in the day. We're going to actually start out with this class around 1600, which is kind of interesting to me because like 300 years from now, you're taking Deacon 1, you're still going to start at 1600. Someone said that back in 1800. You don't care. Anyway. Okay, so temperature back in 1600. Now they have a pretty good idea what temperature was, but now they're starting to try to measure everything. So what they did was they decided to use a scale, a linear scale of what? Volume. All right, so let's make a line. A times volume plus B is temperature, volume of the gas. Right? Now that's easy. That makes sense. You know that a lot of things heat and shrink with temperature, and there's some weird like metamaterials or whatever that actually will shrink with shrink with heat. Okay, those are weird, but some people do have those things. But for the most part, things expand when hot, and nothing expands more than a gas. So that's like a good thing to try, right? Remember 1600. The only thing is they need a balloon. They have balloons back in 1600? Yeah, they did. Just they didn't have rubber, right? No, they did not. Guess what they were made of? What was that?
Fabric.
Yeah, pretty much, yeah, leather. Yeah, they had leather. Actually, I went to a Da Vinci thing last night, and Da Vinci has made a little, what do you call it, a little life raft thing out of leather. So, yeah, so they had waterproof and airproof leather. It's just that I can imagine being a little kid, and you go to a birthday party, and it's like this cow head balloon, just like, I'm dead, So they did have those. They did have balloons, and this is how they started to define temperature, actually define the temperature scale. All right, now, again, I'm sorry, I should have covered this last time, but I spoke too long. It's a line, it has two unknowns, a slope and an intercept. So let's make two measurements, and let's say one is at 0, and at t equals 0, we're going to calibrate this line. The volume, let's call it V0. And of course it was a number, it's 5 liters. I don't know what it was something like that, it doesn't matter. Now again, in one equation with two unknowns, let's boil water, right? We can freeze water, we can boil it, that makes sense. And the volume we measure in our horrifically serial killer-esque balloon with a cow head had a volume, I'll just call that volume V100. And that's what they measured. Yes, they were numbers, I don't know what they were. You're actually going to do this exercise in PChem Lab, by the way. I wrote the module, so now you know why I'm doing this. Okay, so two equations, two unknowns, fit them, let's get rid of A and B, or more accurately, you'll do it. If you feel like, I'm not going to put this on a test or a homework or anything. If you're not quite sure how I do this, just practice it. It's just algebra. You have algebra in middle school. Okay, so what you get is, again, getting rid of A and B with these numbers. You get this. This is essentially the slope, and this is the intercept. And again, just try to yourself, put these into there and figure it out. And so there you go. So what they found was, again, here's a little aside. They found that the intercept, I guess this is minus the intercept, 100 V0, that's where that comes from. Again, the intercept, V100 minus V, whatever units they were using, was equal to 273.15. Sound familiar?
Kelvin.
Right. It certainly does. Yeah, it sounds right. So here's what I'm going to do. Now, I try not to do this. I try not to write over my own equations. Let me multiply by V0 and divide by V0. Okay? And why am I going to do that? Again, I won't do this like ever. I'm breaking one of my bigger rules. I try never to write over my own stuff as a derivation. It's very annoying. Okay, so what you get, so let's plug that factor in, 273.15, and don't worry so much about decimal points. I'm not, we understand about rounding errors, we've heard of them before. Okay, and I'm just bringing that V0 through. Okay, so that's what they got. Again, cowhead balloon, boiling pot of water, yada, yada, yada. Little factoid, don't write this down. Celsius actually called 100 degrees cold water and 0 degrees hot water. It's funny how we do that. They switched it a couple of years later because that just doesn't make sense. And there you go. Now, you don't care, do you? You'll care in Beacon Lab when you have to do this, and what you can find actually if T happens to be minus 273.15, therefore, and this is another thing, look out folks, I use this a lot, this means therefore, V is what? Right, so you see minus 273.15, therefore this factor is? 0. How do I make it 0? Volume is, just said it. 1. No, 0. Volume is 0. Remember, V0 is like 5 or something. Okay. So if they figured this out, now they could not even get close to minus 273. They really couldn't do better than 0, right? Ice water. Thank you, snow. be years later before they discovered refrigeration and then learned to kill themselves with it. Refrigerators are some of the most dangerous objects that exist. Think modern engineering, but they're not so deadly anymore. I'll tell you about that one another day. Okay, so here they are predicting that at minus 273, even though not even close to that, the volume of the gas would be 0. So what? Well, what happens if you go lower? Volumes are... What would the volumes be if you went lower than that? They're what? They're smaller. How do I make something smaller than 0? It becomes negative. It becomes negative. Right. If you are below minus 273, this V has to be a negative number. Now, you don't have to question reality to itself to think, does negative volumes exist? Anyone? No, there is no such volume smaller than 0. There are no pressures less than 0. I'm going to use that a lot, by the way. Now, you know that. You just have to think about it. Don't write it down. You know that. There's no negative volumes. There's no negative pressures. They don't exist. So, they figured out the absolute temperature scale, that you simply cannot go below minus 273, which has been proven time and time again. And in fact, when we do quantum, you can't know where something is and how fast it's going. If you freeze something down to minus 2, close to this, then you know how fast it's going. It's not moving at all. Therefore, you can't know where it is. How does that happen? Nature will actually take an atom and spread it out. We've actually done this before. We can image atoms, and when we get them really cold, the atoms appear bigger so you don't know where they're at. Oh, come on, that's cool. Stephen Hawking's cool. It's like a robot, come on. All right? So I'm going to cut that. Right, so anyway, you're going to do this. You're actually going to make these measurements in the P-Chem lab and show that that's the case. All right, a little lame, yes. Let's do a harder one. Let's do pressure. And remember, we are going to spend a lot of time about talking about a gas expands, a gas contracts. Those are going to be simple. A gas expanding will be like a chemical reaction, maybe because we're making more gas, but we won't start there. We're going to just do gas expands and gas contracts. Chemical reactions, and then we'll actually get to chemical reactions. So let's do pressure. Build a phenomenological model for pressure. Now, you should have learned, hopefully in high school, that there are molecules and atoms, and that they hit walls of things, and that's where pressure comes from. So let's build a box, and it will have length L. And I'm an okay drawer, not too bad, so a little painful, but okay, a little box, and I'm going to put an atom in it. And again, I'm trying to figure out pressure. And I know that molecules are atoms, so we'll make it like helium. That's an atom. I know that they hit the walls, and that's what I call pressure. Right? That's simple. I know that's for certain. So now I'm going to try to connect this molecule, understand this molecule by my macroscopic observation of pressure. Again, that's one of the bigger goals of this class, is to take things I can measure with a thermometer and a cowhead. I mean, they did it. A cowhead balloon, and understand molecules. That's kind of another one of the goals of this class. All right, so and I'm going to use a phenomenological model of something hitting a wall. Now, I know that pressure is force. Sorry, my handwriting's not so great yet. Force per unit area. My handwriting will get better. It doesn't sound weak. So now I need to figure out what the force is. Area is obviously L squared, so I'll make the box length L. So I know what the area is. It's L squared. Force is mass times acceleration. And this object, this helium, has a mass. I can look it up. It's bouncing off the wall, so I need to figure out that's a change in acceleration. All right, now, so that's what I'm trying to get to is force. Area is easy, force. Let me try to figure out what force is. I'm going to do it via momentum. And especially in P-Chem 2, remember that we use the letter P for that. Maybe you don't remember that, but if you do, it's fine. Okay. Now, my curly V will be velocity. Big V will be volume. Sorry, we don't have enough letters for this class. This is the problem. Okay, MV. All right, but now what I need to do is it's hitting the wall, so it's changing. Therefore, delta P is, I need to get to acceleration, so I need, acceleration is a change in velocity. I'm going to go through momentum. I hate that this happens. A lot of times I start a derivation and you're like, what the heck are you doing? And then I get to the end, you're like, oh, well, that totally made sense. So you just got to wait some of these out. Okay, so final minus initial. So final, sorry, I almost used a different type of V. I'm going to try to be careful. Okay, it looks like it's moving MV to the right, final minus initial. Look at that, it's moving to the left. And I'll just say that it had the same velocity. Remember, that's an elastic collision. Don't worry about remembering that. I don't really remember that. I actually made it up. So there we go. So this is 2MV. And I know this isn't perfect. Maybe it didn't bounce off the same velocity, but that's why this is a phenomenological model. Okay, now I happen to know, again, I'm trying to get through to force, which is mass times acceleration. I know that, since I already know what the derivation is going to be like, I know that I need to define time. Again, phenomenological model. I need to figure out how long it took for it to change momentum. And that's not particularly well defined. It's like, well, I don't know, how long did it take to hit the wall? I don't know. I'm just going to come up with something, because what else have I got? Now, I can imagine, I'm looking at this, and I'm thinking, if this thing has traveled at least 2L, 2 lengths, then it had to hit a wall. You may think, well, if it travels more than 1L, it had to hit a wall. Actually, it could go catty corner. Right? So I know that if it goes 2L, it had to have hit a wall. And but this is time. That's distance. I need to wipe out distance and be left with time on top. So I need to divide by meters and multiply by seconds. So and then I'm going to divide that, so I have to take that one over. So it's meters per second. What's that? Velocity, right. Divide by velocity. Now I've got meters on top, seconds on top, times meters. I'm left with seconds. Okay, that works. Okay, and I don't know why, so that's time. I don't know why I wrote equal sign. That's just stupid. Okay. Now I'm almost done. Let's define force, which is mass times acceleration. Okay, I'll just write it out in A, acceleration, whatever. Now, I happen to, I remember some of my basic physics. That's M times delta V over delta T. And M is a scalar. And now I got to remember that acceleration is delta V over delta T. I don't remember that actually. No, you don't. If you need it, it's in the cheat sheet. Now, M is a scalar, which is the fancy way of saying that it's a number. Okay, so I can bring it into the delta sign. It doesn't really mean much, but now I recognize that as delta P, which I've just defined. See, I told you I knew the endpoint, so I knew what my start point should be. These generally are done backward. Okay, and therefore this is, sorry, I painted myself to a corner. Okay, what is it? 2MV, delta T is 2L. Now the V's on top. Okay, and so that's mv squared over L. Whoop-de-doo, but that's like, okay, so what, but remember, I wasn't really trying to get to force, I was trying to get to pressure. Okay, therefore pressure is force over unit area, so mv squared. Now I've already said that area is L squared, which is mv squared over L to the 3. And I know you can't see this, I'll move this up in a second. So it's mv squared over the volume. And I'll spell that out because I know that I don't know what V is anymore. Oops, sorry, you can see that. And therefore, well, that's it. So mv squared over volume. Well, okay, that's the punchline. I'm done. You don't care, do you? Okay, hold on. Let's make it a little bit more easier. PV, I'm going to bring volume over, is mv squared. Now, when I get stuck with understanding the meaning of, I've thrown this at you as a test, and I'm like, what's the deeper meaning? And you're like, what? You should do that. Here's now, I don't know exactly what to tell you what to do, but here's a hint. This might help. Look at the units. figure out what the units are, and that generally, there have been lots of times in my own PhD education where I was looking at an equation and I had no idea what the heck was going on, because we do that, and units help me figure it out. So, okay, kilogram, right? Remember that mass is kilograms in SI. Velocity, kilograms meters squared per second squared. And here, I'll toss this up. What's that? What's that called? Kilogram meter squared per second squared? Joule. Yeah, it's a joule. Again, sorry for my crappy handwriting. Let me toss that up so you can see the whole thing. Yeah, it's like dragging a cat. Because that's what that's like. Okay, there you go. Pressure times volume is energy. Right? You still don't care. Okay, all right, we're still doing phenomenological models. Now, here's the point. Pressure times volume is something you've seen quite a bit, but did they ever tell you it was energy? Did anyone actually, seriously, did anyone actually know that P times V is energy? I actually did say it last time, so you actually should all be raising your hand. I'm embarrassed for it's both, so I'll just move on. Now, what did you learn? PV, I'll try to look down. What did you learn it was equal to? NRT. Right, NRT. Okay, what are the units of NRT there for? They have to be joules too. You can't have one unit equal to a different unit. No, you can do that, but that would be an F for the course. So joules better equal joules. Units don't work that way. Units add up to the same joule. They can multiply. Units can be multiplied and divided to equal new units, but they have to add or subtract to the same unit. And technically, these are being, I can take PV minus NRT equal to 0, so that counts as being added or subtracted. Joules. Okay, so the significance is, this is one of the first lessons I want to get across to you, is that this phenomenological model allowed me to define pressure, which was kind of nice, but in the process, I can measure pressure, and now I can tell you something about, I might be able to figure out the mass of the molecule, which is kind of incredible because that's kind of incredible, it just is. But I can get something more out of it. I can see that pressure times volume actually has units of energy. I guess I could have figured it out other ways, but now it's like very spectacularly in my face. And now I see this equation, and I realize that this is just actually a statement of conservation of energy. PV equals NRT is something, again, this is the point of the course. PV equals NRT is something that was just forced down your throat and you just accepted it and just tried to memorize it. What I'm telling you is, where does it come from? It's actually a statement of the first law of thermodynamics. Energy is equal to energy. They have to be equal. They have to be conserved. And so it's the first law. Energy cannot be created or destroyed. And you just thought I was bouncing a molecule off the wall, right? And you're wrong. I was drawing a molecule bouncing off the wall. It's different. But anyway, so this is the kind of thing, really? Okay. I thought it was me. And because it is. You're wrong. But this is the kind of thing that you get out of this class, is doing things with equations and learning things that you didn't really know about before. And that is just kind of useful. And there'll be other examples I think you'll find a little bit more interesting. This is a little dry. Let me indoctrinate you to a couple other things. Remember, units add and subtract to the same units. That's going to come up on the first test. I'll give you more example problems as homeworks go on. You do need to be familiar with SI units. And so let's do pressure. And remember, that's a Newton. Now, I do expect you to remember these, but they are going to be on the cheat sheet on the exam. So that'd be a Newton per meter squared, because those are standard SI units. But a Newton, okay, that's the name for another set of units. I happen to know that a Newton is a kilogram, because kilogram is the unit of mass in unit of mass in SI. And a Newton is almost a joule, except that it's divided by a second. And then it's still divided by meter squared. And kilogram, no. I am an idiot. I got meters and seconds confused. Sorry, right here. Right, force times distance is energy. So the kilogram meters per second squared, whereas a joule is kilogram meters squared per second squared. Sorry about that. And so that means that a pressure, which is actually in pascals, It's actually a kilogram meter per second squared. Let me make sure because I'm not that in hundreds. Okay, again, my point being that I will have all this kind of jazz if you need it on the cheat sheet on the test, but it's going to be kind of good if you know them. Question?
The meters squared on the bottom. Wouldn't that just be meters? Oh no, because the Newton is the kilogram per meter. Never mind.
Right. The thing I was thinking up there a little bit earlier. All right, so we're set. Okay, another thing is, now I hate this one, but I have to teach it. Multiple units. Unfortunately, it's traditional in this class to throw multiple units at you, and I think that's stupid. We should all just use one unit, which of course is American, pounds, and miles. Okay. Like, I hate this, but it's on standardized tests. If you take GRE, God forbid you take the GRE and make some money in your life, then they will throw these kinds of questions at you. I would be remiss in my duties not to cover them, even though I don't want to. I have to do that. So remember, an atmosphere is 101.325. I don't expect you to remember. 101 is fine, all right? I'm not going to, you're not going to lose points, whatever. So you got it. It's kind of easy to remember, though. It kind of sticks in your head, right? And that's 760 torr. So I do have questions where I throw different units at you. Okay, another one that you already have on your present homework is 100 kilopascals is equal to a bar. Okay, this another unit of pressure. Remember that standard SI is a pascal, so that's multiplied by 1,000. Note that when it comes to BV equals nRT questions, or the harder ones that are actually on your homework that we're going to cover on Friday, you do need to just stick with this certain set of units. Like, personally, I like kilopascals and liters, because kilopascals is not standard SI. It's off by 1,000, but liters is not standard SI. It's too high by 1,000. Too high by 1,000, so they cancel. They'll cancel in all the questions that I ask when it comes to gases, right? So remember, kilopascals, 101.325 is 1,000 times too small compared to a pascal. Liters, the SI units for volume is meters cubed, not decimeter cubed, which is what a liter is. But notice the effect cancels, and that means that I use 8.314 joules per kmol for R. And so when I get bars or torrs, I just convert to kilopascals. If you give me meters cubed, I'll convert it to liters. I just do that instantly. I do the work and I get the right answer every time. So just try to stick with something. I like the ones that I use. Okay, anyway, now that we're still in PV equals nRT land, and again, I warned you today was high school level, and tomorrow, Friday, spectacularly not. Let me just go over state variables and with a dramatic example. I hate these dry definitions, but I do need to go over them. And so I need to tell you about state variables. And state variables are basically PV, N, and T. And so let me write that down. So state variables. And just a warning that we are going to spend a lot of time doing, as I mentioned, gas expand, gas contract. That's our simple chemical reaction. And that means PV equals nRT, and the harder equations are going to come up a lot. So N, T, P, and V. Okay, the point of these suckers are, and I'll just do this with example, that a balloon, so remember this is an aside, often when I'm doing this you don't really need to write this down. A balloon has about 0.1 moles of gas, that's about a liter, 10 to the 23 number of atoms. Okay, we're going to do helium, right? So that's about 10 to the 23 atoms of helium. Now, we can do things on computers that can model. So I want to know everything about this balloon. I want to know if it can drive a piston. I want to know if it can turn a turbine, if that's useful. So I need to know what it can do. And so to do that, I need to know about all 10 to the 23 roughly atoms in it. And all I would really need to know is where they're at and how fast they're going. And so that's 6 bits of information for every atom. Hell, let's just say it's 1. The problem is that the age of the universe is, you see, you don't need to write this down. universe age is roughly 4.1 times 10 to the 17 seconds. Okay, so that means that for me to process, it takes me a second to process every bit of information about the atoms in the single balloon. It's 4 million times, is that right? Yeah, 4 million times the age of the universe in seconds. Oh, you should use a computer, Dr. Jackass. And so I do that, and of course a fast computer is about 2.5 gigahertz. And now you're right, I only need to spend 0.1% of the age of the universe to understand this freaking balloon. All right, again, I'm not going to do that. Besides, the balloon blows away, and I've just wasted my entire universe while I'm doing that. Okay, now the point is that while it is true for me to tell you everything necessary, everything you could ever want to know about that balloon, I can tell you with these numbers. But it is exactly equivalent to tell you these numbers. Now, there's obviously a greater level of detail in having all this information, but for anything practical you want to do, remember I said turning a turbine, moving the piston in the car, this is actually sufficient. So I'm going to blow this, right? So anyway, that's the point of state variables. And the purpose of an equation of state, it connects them. Okay, so you'll get used to my way of anyway. All right. So equations of state connect them together. Note that means that in any, what you care about, right? Homework problems, test problems. I always have to give you 3, but I won't give you a 4. Notice that you're missing R, but R is 8.3 once, whatever. It's on the cheat sheet. So there you go. 3 things give you the 4th, and their job is to connect them together. All right, now as I mentioned, today is high school level, so we're going to do PV equals nRT. Because PV equals nRT is going to come up a lot. Now it comes into play as a small part of a really big question. So again, yeah, I'm asking some high school level questions, but only once. To understand where PV equals nRT comes from, I can derive it phenomenologically. It can be derived. There is a way to do it in grad school that I cover with grad students, obviously, that takes about 2 days and about 4 or 5 boards of equations. Or you can do it the way I'm doing it now. The way I'm doing it now is phenomenological. And it starts with Robert Boyle. So Boyle's law. Robert. So I'll just write the different laws. And there's laws and there's a couple more. Boyle's law. Boyle was an alchemist. They didn't have chemists back in, this is the 1600s that he was alive, mid-1600s. I told you we were starting in the 1600s. He was not a chemist, he was an alchemist. They didn't have chemists. They had to have the A there. It was important. And he founded the Royal Society, which is where we get all academic societies today. Anyway, I'll take that back. By the way, universities come from? Anyone know where universities come from? Where are these modeled after? So he started professional societies, universities, the church. We're modeled after the church. We even have the structure of the church. When you get a PhD, you get, the ritual is, as was done to me, put a cloth around their neck. It's called hooding. It's actually modeled after the priests when they were the only ones who could write. That's why it's modeled after the church. They would get cold in their monasteries because like rocks and all wet and stuff like from movies. So they put cloth around their neck. So anyway, so that's where universities come from. Okay, so what he came up with, not J-Law, but B-Law. What B-Law came up with was, so if you're given a certain mass and temperature, okay, again, so you know, I'm just kind of doing this more to introduce you to my shorthand. I don't really have a choice. Okay, if you have a certain mass and temperature, pressure times volume is constant. Okay. So that means that basically, so he's got a balloon and it's at room temperature, and if he squeezes it, the pressure increases. That's what he figured out. Good for him. Cowboy balloon, yada, yada, yada. So that's what he figured out. 200 years would pass before anybody figured out anything else to do with this cowhead balloon. And that was Jacques Charles. Charles was long. Jacques Charles. Oh, yeah, okay, now this guy was cool. This guy's legitimately cool. 1800, so things are a lot less messed up. I don't no internet, so who cares? But he was messing around. At this point, they had chemicals, and they started doing chemical reactions. He was dissolving iron in sulfuric acid, I think, and making hydrogen gas, which he used to fill balloons. He took the first balloon ride. Well, they think he took the first balloon ride. The documents are spotty. But could you imagine the first person to ever get up higher than a tree? Now remember, they couldn't build a building higher than 4 stories. Eiffel Tower was like one of the first things ever built bigger than 4 stories. And worse, only poor people lived at the top. You know why? Not the Eiffel Tower, I'm just talking buildings. 4-story buildings, only poor people lived at the top. You know why? No elevators. Fire kills everybody. No one cares about it. So only the poor people lived on top. They had to go up the stairs. So, yeah, you know. So anyway, imagine that, being the first person to get higher than a tree. Not higher than a kite, but higher than a tree. So what they think happened was, now it's known that this happened, they just don't know quite for certain whether he was in it. He supposedly takes the first balloon ride. This is around Paris. His name is Jacques Charles. And when he gets outside of Paris, which was walled up at the time, it's one of the reasons for the French Revolution, he's flying over the peasantry. And remember, these people's education was, "Hi there, Jock, you see that cow, see that hoe? Now you got a PhD, right?" So it was plow technology, that's all that they knew. Now what happens when you get this 18th century rube who knows nothing but the plow and the cow, and he sees someone flying overhead? All right, 2 options, angel or demon. Guess which one they chose? Yeah, demon. He's looking down now. He knows these people are pretty stupid, right? And he sees them following him with torches and pitchforks. And he pretty much figured out which one they went with, which is this, right? He figured out that they think he's a demon. And so he, fortunately, somehow the wind blows him further away from them. He crash lands at a field, runs off, and he did survive, while the townsfolk proceeded to destroy the world's first, wasn't a hot air balloon, but first lighter than air balloon. And so they wiped it out. But we figured it out again. So anyway, so that's who he was. So he's kind of an interesting guy. 200 years would pass, and what he figured out was if you were given a certain mass and pressure, therefore V is proportional to T. Now, given that he was obviously a pretty bright guy, he came up with another one. Sorry for this weird board. Given mass and volume, therefore P is proportional to T. Whatever that means, proportional. Okay, last one. Sorry about this. Yeah, I really don't like this board. Maybe I'll try to give us a new one. Was Avogadro. Okay, and Avogadro, okay, let me tell you about him. Yeah, he's Italian. This is 1811, so they are moving kind of more quickly. His name was Lorenzo Romano Amido Carlo Avogadro. Anyway, he had a bunch of names to please the family. I mean, look, your families do it too, right? And he was he was the world's first political pundit. I'm glad he's dead. So anyway, and now here's the thing. He doesn't have a law. Notice I didn't write law. It's a hypothesis. He has a hypothesis. Let me write it down. Let me write his hypothesis. And let me see. Given a certain temperature and pressure, therefore volume is proportional to the number of moles. Okay, I hope that's not hard. That's Avogadro's hypothesis here. Let me just toss that up there so you can see it. It's a hypothesis, get this. This slays me. It slays me every time I cover this. It's a hypothesis because technically molecules, because the philosophers decide this stuff apparently, I don't know why, because you cannot see a molecule with your own eyes, they are hypothetical. If they are hypothetical, you cannot have a law. And again, they're hypothetical because you cannot see them with your own eyes. Even though we have machines, I just told you about that, we have machines that can image atoms and molecules like perfectly, well, perfectly, maybe the person's ever going to care, as well as your own eyes work, I don't think that they're hypothetical. But to a philosopher in a Starbucks, because that's all we can afford, they're all poor. They're hypothetical, so Avogadro gets the hypothesis. Okay, now the sum of this stuff is, well, here, let me draw this behavior, and these are all isotherms. You're going to see a couple of these, so I'm just going to draw them out. Plus, probably should know about them. So an isotherm, let's do a therm, and this is sorry, I'm not drawing super great today. Isotherms, of course, isotherm means that there's one temperature, and that means I am only left with two other variables, which is volume and pressure. And of course, this would be a low temperature. And you can imagine I've done this on the test. I draw this. Is this a higher or lower temperature? Higher, and you can tell because it's at higher pressure. Okay, and then I can do an isobar. Now, remember, bar is a unit of pressure, so the pressure is constant, and therefore I'm only left with V and T as variables. Now remember, we're at Charles's law, and because these are across the aisle, not on the same side like Boyle, these will be lines. And okay, let's do this one. All right, so it's a linear behavior. I've drawn two different pressures. Is this one the low or high pressure? Now, it's at a small volume. What do you do to get small volumes? High. Right, this is high. And obviously the other one's low. And the isobar, now let's do an isocore. And this one is probably kind of new. I'm not sure where that word comes from. But since volume is constant, that leads to P and T. Again, linear behavior from Charles's law. And, sorry, that's rather flat, isn't it? It should be totally flat. Okay. High or low volume? Let's do this one. High or low volume? It's at low pressure, so high volume. Right. Yeah. High volume. Now, high volumes have low pressures, right? It makes sense. Just think about it. I could put this on a test. I've done it before. You probably already know that because you have my test. Now, anyway, the way that you can put PV equals nRT together with this is note that from Boyle's law, you got PV is equal to a constant. So P and V ought to be on one side, but you also know that they're proportional to number of moles by Avogadro in temperature. And there you go. So I'm done. Huh? Am I missing something? Okay, here's how to figure it out. Joules, Kelvin, moles. Those units don't work. R's purpose is to make the units work. So nRT, right. But notice that's what R's job is. It's not some crazy, it's hard to describe, but, and I'm not going to get to show you in this class, but remember that our units we came up with back in like 1600, and like a meter, it's about as high as my leg, right? A liter, that's a meter. A liter is about as much water as I can reasonably carry. All of these are human units. If we actually worked with units that make sense to science, we wouldn't have any constants. We wouldn't need them. So that's kind of neat. They would all be the number one. So, but anyway, I don't actually get a chance to teach you how to do that kind of stuff. That's kind of neat. Okay, last bit I want to cover is gas mixtures. Again, this is high school level. This is Dalton's law. And then I'm going to give you a homework help. I don't know why this is a law, but the point of this is that this is for gas mixtures. And what it says is that the whole is the sum of the parts. So what this means is that you can actually take a gas mixture and figure out all the individual characteristics for each gas and then add them up to get the whole. Okay, a bunch of words, you're struggling to write it down, don't. Here, let me write it out mathematically. Pressure is equal to, let's say we have a gas mixture of A, B, and C. Sorry, this is the kind of thing I do when I write and talk, so I try not to do it. So what you can do is sum up the parts, the individual partial pressures, to get the whole. And you happen to know, of course, that the partial pressures will be equal to the mole fractions times the total pressure. And of course, I'll write that down in case you don't quite recall. I know you're having trouble seeing this. So this would be the number of moles of A over the total. Okay, anyway, look, you've had this before in hopefully high school chemistry. I just want to remind you about it. And we're going to use this a lot coming up when we do actual chemical reactions. And we're going to do chemical reactions in the gas phase because that's easy. So just want you to remember this. Don't want to say anything else about it. Last bit, our homework help. I just want to point out to you that in my class and any others, when it comes to gas questions, now folks, we do have a class that comes after me. Normally that doesn't happen. So if you have questions, let's just try to struggle out of the room and ask me there. I know real quick, I know you're ready to go. Let me just point out that all for problem solving, like on your present homework, you always start, every gas problem is actually two problems. One is a setup. You establish 3 out of 4 state variables, and then you change one of them. So let me give you an example. A gas is at 300 K, 3 bars, and 10 liters. And the volume increases when it's heated. Okay, that's 2 statements in one. It's actually 2 questions in one. Let me begin with the first part. A gas is at 300 K, 3 bars, and 10 liters. What are you missing? Pressure, volume, temperature, you're missing moles. Right. Now, once you get moles, notice the second part. The volume is increased and heated to this. Okay, now you know V, N, because you figured it out. You figured it out from here, and T, leaving pressure behind you. That's what the question is. So again, remember that all these gas-based questions are a setup that's left you to answer one question, which is the missing variable. The answer to the actual question is actually a second question because something's changed, where you use the information from the hidden question, the first question, and you apply it to a new condition in the second question, and there you go. So just look out for that. That's how these work.